Hello everyone, it's my honor to be here to introduce my paper. Today we want to talk about the paper and racial visual segmentation using multi-scale generated adversarial network with class activation mapping. It's clear to see the purpose of this article is to accomplish racial visual segmentation effectively. So why do we want to do this topic? Racial visual segmentation has been a long-standing topic in the medical imaging. In the treatment and evaluation of the racial disease, the segmentation of the racial visuals in the fundus is essential. However, traditional medical imaging processing mainly relies on the personal experience of experts to analyze and process images. But this method is inefficient and subjectively affects the analysis results. So, it is necessary to use the computer to automatically process the racial visual segmentation imaging. So, how to use computer to do this task? The methods of the racial visual segmentation consist of the supervised learning and unsupervised learning. Supervised learning requires training through the original fundus images and the images of the blood vessels manually labeled by the expert. Unsupervised methods don't need label. Common supervised learning methods applied to the racial segmentation include the support vector machine, random forest, multi-layer perceptron. The common unsupervised learning methods consist of the template matching, multi-scale analysis, and visual checking. Looking through the literature, we found that the adversarial neural network didn't have a lot of researches on fundus image segmentation, and we have used the generative adversarial network to accomplish the task of the image style transfer. And also the visual segmentation is also a kind of the image style transfer. So we think the generative advisory network could have a good effect in the task of the racial visual segmentation. However, existing methods commonly have three problems. The first one is model usually omit the macro visuals. The second one is the model can generate the false positive visuals. And the third one is there are too little data. In order to solve the first and the second problem, we use the multi-scale generative adversarial network with the class activation mapping to achieve efficient segmentation. For the problem of the small amount of data, we introduce a novel data augmentation method, which can generate multiple samples by cut and paste from other samples. This method increases the diversity of the samples and improves the robustness of the model. And this is the structure of our model. Firstly, let's talk about what is generative adversarial network. We call it GAN. For normal neural network, it only has one network, but GAN usually consists of two networks, generator and discriminator. A generator will generate the images and transport it to the discriminator. Discriminator judges whether this image is real. If it is real, then give a high score to image. If not, give a low score. And the loss will make the generator update the parameter, and the discriminator will update itself too. So, generator and discriminator update themselves through learning from each other. That's why we call it the generative adversarial network. And in this picture, you can see, firstly, the input image was transmitted to the generator. Then the generator generates a new image called the generated image. After that, model respective pack two groups into the discriminator. The first group are input and generated images, and the second group are the input and labels. For the first group, the generator will give a low score. This group into the generator. Generator will give you a low score because the generator think the generated image is not real for the input image. And for the second group, labeled and input groups, they transmit to the discriminator. Discriminator will give this group a high score because they think the label is real to the input images. And for example, we give the generated image a score of 0.2, and we give the label of the score of 0.9. So the adversarial loss is the 0.9 subsequent the 0.2, and the adversarial loss is the 0.7, and we transmit this loss to the generator. Generator will try its best to lower the adversarial loss. So it will update its metadata in order to generate more realistic images to get a higher scores of the discriminator than. A discriminator is not that stupid. It will also update itself in order to help the generator generate the more real images. As we can see in discriminator, it has three components: C0, C1, and C2. And it means the discriminator evaluates the generated images through the high resolution, medium resolution, and low resolution, respectively. So we call it the multi-scale. After the discriminator produces the advisory to the generator, generator will update the parameter. So the below structure is the generator. It's clear to see that we use the UNet. The blue one is the convolution. The red one is the upsampling. There are 3 layers of our network. And for each layer, we add the linear attention transformer. The structure of the linear attention transformer is here. Now, let's talk about the data augmentation method. The first line is the input image. The second line is the initial labeled. And the third line is the label after the data augmentation. As you can see, the data augmentation is a method that cut peaks of the area and fill this area from another dataset. And the filled area can be any size. This is small, this is big, and any angle. This is the 75 angle, and this is the maybe 30 angle. As you can see, through this data augmentation method, we can produce infinite in infinite datasets because there are a lot of comparison between two samples. You can use different angle, different size, and either different location to one sample. And this is the input after data augmentation. This is the label after the data augmentation. They are a pair. Okay. And this photo talks about the class activation mapping, which make the people can easily observe how neural network worked. In picture line 2, you can see red line and blue background. And the red line means the model pays more attention to here. So the model will give a higher weight to the loss. For the color closing to the blue, it means the network gives less weight to the loss generated by these peaks. And through this photo, we can easily find that the area of the ratio vessel is red. So our model was trained in the correct way. And this is the picture of the visualization of results of our model. Line 1 is the input. Line 2 is the label. Line 3 is the visualization of our result. As you can see in line 3, the green blood vessels represent the correctly predicted blood vessels, and the red vessels means the real blood vessels that wasn't being predicted. And the blue vessels represent the non-existent blood vessels generated by the generator. From last three photos, we can find that our model can clearly identify the main vessels, and there are very few unidentified and incorrectly identified vessels. It proves the superiority of the model. Finally, this is the quantitative evaluation of our model. We use 4 metrics to evaluate our model, which are accuracy, sensitivity, and specificity, and AUC and ROC. Accuracy, and there are the formula of each matrix. Accuracy and AUC-ROC are very authoritative and intuitive indicators in classification algorithms, which can evaluate the effect of the segmentation. Accuracy is a metric to calculate the ratio between peaks, which are correctly classified, and total peaks in the dataset. Sensitivity, also called recall, is a metric to measure the proportion of all predicted positive samples to all positive samples. Specificity indicates the proportion of the true negative sample among all predicted negative samples. As shown in Table 1, we use quantitative analysis to evaluate our model. It can be clear seen that our model has a good effect on various metrics. The compared model may only focus on certain metrics, such as this one. It only focuses on the specificity, but its AUC and ROC is very low. But our model can complete the segmentation task while ensuring that overall metrics are better, especially for sensitivity and specificity. It can be seen that our model can ensure the segmentation of real blood vessels and can be helpful for auxiliary diagnosis of the medical disease. And that's all. Thank you for listening.